We've spent the last couple of videos getting the general idea of using complex exponentials to analyze steady-state sinusoidal system responses. In this video, I'll introduce phasors. Phasors are used to represent the magnitude and phase angle of a sinusoidal signal as a single complex number. Using phasors greatly simplifies the math associated with steady-state sinusoidal analysis. First, let's do a little review relative to viewing complex exponentials as sinusoidal signals. Euler's identity says that a complex exponential e to the j theta sub a is equal to the cosine of theta sub a plus j times the sine of theta sub a. This complex number can be visualized as a point in the complex plane with a magnitude of 1 and a phase angle of theta sub a. The real part is the projection onto the real axis, cosine of theta sub a. This concept can be extended to time-varying signals. If theta changes with time at some frequency omega, e to the j times omega t is a complex number with a magnitude of 1 and a phase angle equal to omega times the time. The phase angle now changes as time increases and the point moves around a unit circle centered on the origin of the complex plane. The projection of this number onto the real axis is the cosine of omega times time. Graphically, if I plot the real part of this complex exponential as a function of time, I get a cosine function. This is an animation of that process. As the point rotates around the complex plane, the real part traces out a cosine function. This means that we can write any sinusoidal signal as the real part of a complex exponential by changing its magnitude and its phase angle. Conversely, if we have a cosine function, we can create a complex exponential whose real part is that cosine function. This turns out to be super useful when we analyze steady-state responses to sinusoidal inputs. Now let's add magnitude and phase shift to the discussion. Euler's identity still tells us that we can write a complex exponential with frequency omega, amplitude a, and phase shift theta as the sum of a sine and cosine function. E to the j times the sum of omega t plus theta is equal to e to the j theta times e to the j omega t. A and theta are both constants, so a times e to the j theta is a complex number in polar form. It has an amplitude a and a phase angle theta. The point here is that any sinusoidal signal can be represented by a complex number in polar form times e to the j omega t. Since a times e to the j theta is a complex number, an arbitrary cosine function can be expressed as the real part of a complex number in polar form, a times e to the j theta, times a time-varying complex exponential that has unit magnitude, zero phase, and frequency omega. The amplitude and phase information are now neatly packaged in one complex number. To reiterate, a times e to the j theta is a complex number in polar coordinates, but it's a very special complex number. It gives the magnitude and phase of a sinusoidal signal. The magnitude a of the complex number is the magnitude of the cosine function, and the phase angle theta is the phase angle of the cosine function. Since this particular complex number has special meaning, it also has a special name. It's called a phasor. A phasor is defined as a complex number which provides the magnitude and phase angle of a sinusoidal signal. In textbooks, a phasor is usually represented in bold-faced font. However, I'll represent phasors with an underscore, since the bold font isn't easy to represent when handwriting a problem. Phasors are invariably represented in polar form, so a phasor, a underscore, can be written in either complex exponential form as a times e to the j theta, or simply as a at an angle of theta. Phasors are extraordinarily useful since they allow us to solve the differential equations describing a system's steady-state response to sinusoidal inputs by doing an algebra problem. Before I go into more detail about using phasors to solve steady-state sinusoidal problems, let's revisit a previous problem. This is the circuit we were analyzing. The input was a cosine function with an amplitude of 3 volts, a frequency of 50 radians per second, and a phase angle of 20 degrees. We want to find y of t as t goes to infinity. We realized that working directly with cosine and sine functions was difficult, so we converted the input into a complex exponential with the same amplitude, phase, and frequency. The actual input is the real part of this input. We also represented the steady state response of the circuit as a complex exponential with an unknown amplitude b, an unknown phase phi, and a frequency of 50 radians per second. The actual response will be the real part of this signal. The goal is to determine b and phi for this signal. We substituted these functions into the governing differential equation for this problem and got this. The e to the j 50t cancels out, so we can simplify the equation to this. Importantly, the numbers we want, b and phi, are now contained in a single complex number which we can find relatively easily using complex arithmetic. If we divide out the j plus 1 term to solve for the complex number b e to the j phi, we get this. Dividing two complex numbers is easiest in polar form, so I'll convert the denominator to this and do the math. The magnitude b is 3 over root 2, and the phase angle phi is negative 25 degrees. The sinusoidal response is a function of time. Y of t as t goes to infinity is then 3 over root 2, the magnitude, times the cosine of 50t minus 25 degrees. Notice that I've already snuck phasors into the solution of this problem. b times e to the j phi is a complex number that provides the magnitude and phase angle of a sinusoidal signal. So this is a phasor. But now let's revisit the problem with the phasors explicitly included. If we use phasor notation in this problem, the input u of t is a phasor u underscore times e to the j 50t. The phasor for the input is known. It's 3 times e to the j 20 degrees. In phasor form, the output y of t is a phasor y underscore times e to the j 50t. The phasor y underscore is unknown. We need to determine its magnitude and phase angle in order to determine the response y of t. If we substitute these expressions into the governing differential equation, we get this. The only difference between this and our previous approach is that I've used phasor notation to represent the magnitude and phase angle of the output sinusoid. The analysis is the same complex arithmetic as before. So the output phasor y underscore has a magnitude of 3 over root 2 and a phase angle of negative 25 degrees. The output phasor y underscore gives the magnitude and phase angle of the output. Since the frequency of the output is the same as the frequency of the input, this is the circuit response. Notice that the frequency of the output disappears when we divide out the e to the j 50t term in this step. We need to go back to the original problem statement here to determine the frequency of the response. It's easy for the fundamental ideas in phasor analysis to get lost in the mathematics, so I'm going to take a moment to review the overall approach. In steady state sinusoidal analysis, all of the signals in the circuit are sinusoids with the same frequency. All of these sinusoids can be written in the form A, an amplitude or magnitude, times the cosine of omega, which is the frequency, times time, plus a phase angle, theta. The amplitudes and phase angles of all of the sinusoids in the circuit can be different, but they all have the same frequency. Our goal is to determine the amplitudes and phase angles of the desired unknown signals in the circuit. The math gets easier if we use complex exponentials to represent the sinusoidal signals in the circuit. The form of the complex exponential we'll use is a phasor, which contains the amplitude and phase angle of the signal, multiplied by an e to the j omega t function, which tells us the frequency. The real part of the complex exponential is the physical signal we need. When we substitute the complex exponential terms into the governing differential equation for a linear system, the e to the j omega t terms will cancel out. The resulting equation is then no longer a function of time, and it'll be a purely algebraic equation with complex coefficients. We can solve this relationship for the unknown phasors, which gives us the magnitude and phase angle of the sinusoid that we want. A graphical representation of the phasors representing the signals in a circuit is called a phasor diagram. This can be a useful tool to visualize the relationships between various signals in a circuit. A phasor diagram is shown in the complex plane. The phasors are represented as arrows in the complex plane. The arrows indicate the relative behavior among phasors, so they can be used to indicate the effect that the system has on the different signals. For the RC circuit example we've been working on, the input phasor, U, is 3 at an angle of 20 degrees. We found that the output phasor, Y, was 3 over root 2 at an angle of negative 25 degrees. This is a phasor diagram of the two phasors. The phasors are labeled U and Y, and their magnitudes are shown, 3 and 3 over root 2. Likewise, the phase angle between the two is also indicated on the diagram. 20 minus a negative 25 degrees is 45 degrees. This figure makes it easy to interpret the effect the circuit has on the input phasor. The circuit scales the input by 1 over root 2 to get the output, and the output lags the input by 45 degrees. Here are a few notes on how phasor diagrams are typically represented. The lengths of the phasors indicate the magnitude of the sinusoids. These lengths, however, are generally not drawn to scale. In fact, since our phasors can represent either voltages or currents, they may not even share the same units. In lieu of being able to scale the lengths, the magnitudes of the signals are labeled directly on the diagram. The phase difference between the phasors is also labeled on the diagram, since, as with the magnitudes, the angles will generally not be drawn to scale. This corresponds to indicating the time difference between the sinusoids. Now let's take a look at how to interpret the information the phasors are giving us to understand what's happening in the real world. This is the phasor diagram for our RC circuit example. The corresponding sinusoidal signals will look like this. The input signal, U of t, has an amplitude of 3 volts. And the output signal, Y of t, has an amplitude of 3 over root 2 volts. The output signal lags or follows in time the input signal by 45 degrees. Notice that this figure doesn't really indicate an absolute time, since it's fairly arbitrary where t equals 0 is. Remember that we're looking at signals in the steady state, so time has gone to infinity anyway. What is important is what's happening to the two signals relative to one another. The biggest benefit of using phasors in steady-state sinusoidal circuit analysis is that writing the differential equation for a circuit is no longer necessary. With phasors, we can treat capacitors and inductors exactly as if they were resistors. I'll talk about this approach in the next video.